Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at ANSYS with Ankur Gupta, who's going to talk today about the impact of voltage and process variation on timing. So Ankur, what sort of problems are you starting to see with process variation and the impact of voltage?
So at lower geometries, we are seeing process variation and voltage both impacting the expected frequency that you have in mind as you're designing your chip.
So where are you starting to see the problems actually showing up when you're getting called into these customer sites?
Customers call us in when their chips are on silicon not meeting expected frequency. And that's where the question comes is it because of variation? Did it not get modeled correctly? Is it because of voltage drop? Is it because of the impact of voltage drop on timing? Where exactly is the source of the problem is really difficult to figure out now because of excessive impact of process variation.
And so this is really the intersection of power, performance, and manufacturing, right?
Yeah, exactly. What you're designing for is always power, performance, and area. But you have to account for the expected variation because of the devices, and that's the manufacturing element. So there's methodology that you put in place, but ultimately methodology plus accurate modeling of the variation from manufacturing, from process variation is what ends up giving you the maximum frequency, the highest yield that you're after.
Is there a big jump from moving from 1614 down to 10.7, and will there be yet another one at 5?
What we are seeing in our customer base is from 1614 to 7, the headroom that you have for operating voltage versus the threshold voltage has reduced significantly. So the margins, the old margins that you had, let's say you had 10% margin for IR drop on chip, that translates to a significant portion of your headroom now. So for instance, if you're operating at 1 volt, 10%, 100 millivolts, but if you're operating sometimes the same chips, sometimes at a lower voltage point, let's say 600 millivolts or 500 millivolts, that 100 millivolts cuts into your budget significantly more. To design for that at 7 and 10 has become crucial. At 5, we see the trends continuing. The process variation is significant at 7 already. We expect that to continue at 5. The headroom, we don't see a change in that either.
Why don't you draw this out for us?
Yeah, sure.
So what are we looking at here?
So let's first look at the physics that's driving all of this variability and the impact of process variation and voltage variation on timing. So what we said is, at the end of the day, every chip is designed to maximize yield given the expected variation that you have at the process node that you're operating at. So this maximum frequency versus voltage, if we drew out this curve, it tends to look like this, where the frequency is falling off as you reduce voltage towards the threshold voltage. So I've got a 0.3 volt over here, 300 millivolts as a typical threshold voltage. Now what you notice is the variation so this is the solid curve over here is 50 degrees, and then I've got two other curves at 110 and 0. The variation at about the 1 volt operating point out here is maybe plus minus 5% for the Fmax based on these other temperature corners. However, when you're operating close to the threshold voltage, the variation can be as high as 2x. So that's our problem number 1. If we reduce the voltage, which we know is useful for low power applications, high performance low power applications, and so on, we have to worry about the variation of Fmax with respect to reduced voltage and across different temperatures.
So what happens with normalized frequency versus process variation?
Yeah, so that's a good question. So we looked at the impact of voltage and temperature. Now let's look at the impact of process. So if I plot normalized frequency with respect to process variation, the solid curve over here is frequency variation, normalized frequency variation at about 1 volt operating voltage, and that band is plus minus 20%. The same device operating at near threshold voltage of, let's say, 300 millivolts, look at the spread. This is due to variation. That is a plus minus 2x spread. Significantly larger variation that I have to account for.
So how are people handling this in their methodology?
Yeah, so of course what you want always is to get the highest accuracy models of variation into your design flow upfront as early as possible. But that's not practical. So if we look at a typical design flow from implementation to ECOs to sign-off, the sign-off tools are of course expected to be fully accurate, and you do have the ability to run an accurate sign-off analysis. But earlier in the flow, you apply margins and you make trade-offs. If you look at timing, for instance, during implementation, most timing analyses are graph-based. You've got margin built in at that point. Then when you get to ECO, you're tapering off some of that and you're going into a path-based analysis. And finally, when you are in sign-off, for these contemporary nodes like 10 nanometer, 7 nanometer, even with path-based analysis, you're looking at tens of thousands of violations. How do you fix all of that and still meet your design frequency requirements, schedule requirements, the power performance area trade-off, as we know of it? That's hard, that's challenging. So what you do in sign-off is you crank up the accuracy level of all these models. Liberty variation format allows you to do that. And with that, you get less margin in your answer, so a more real answer.
And the margin impacts both performance as well as power in some of these advanced nodes, right?
Yeah, exactly. There is performance, the impact of margin on performance is due to process variation that we saw. The impact of margin on power is based on what margins are you using for IR drop. So it's really an interaction of both voltage and timing that we have to account for while designing for the best frequencies that we can achieve.
The impact of that is broader because it also affects area, but it also increases the complexity of the chip, because now you have to think about all the extra circuitry that you've put in there. You have to go ahead and debug that. You have to verify it. You have to make sure it all works together.
Exactly right. So if you think about the ECO and the sign-off cycle, that's schedule is driving your chip delivery at that point. For every path that is identified as a must-fix failure, you have to add logic. That logic is impacting your area directly. At that point in your design, it's so well baked that routability resources are scarce. So yes, you're right. It does impact area significantly. It does impact schedule significantly. Contrast that with an answer which allows you to get a real timing number without the additional margin. So if there are 10,000 paths with margin that come down to just like tens of paths with accurate modeling, then there are as fewer paths to fix, lower cost and area, lower impact on your schedule. Life is good.
So out in the real world, as you're dealing with your customers, what are you hearing back from them? What are you getting called in for to help them with? And what sort of problems are you trying to solve?
So in one such case that I can talk about, this is a specific case where there was a failure and the customer went in, looked at the region of failure, cranked up the voltage, and identified about 50 paths to then debug So the cranked up voltage resulted in a functional chip. So then the question was that, all right, what is the cause of the failure? Is it just IR? Is it process variation? So the initial slack of these 50 paths is what I've drawn out here. Then what we went in and did was, this was based on path-based analysis. So we did a path-based analysis plus a very accurate LVF type of analysis based on some modeling of the process. And in most cases, what you would expect is, because you're putting in a more accurate process model, the slack should actually go up because you're peeling off margin. And that's what we saw in most cases, increased slack. However, on a couple of paths, we saw a very interesting reverse trend where the slack was significantly lower. And this can happen because there is variation even on constraints, which are not fully modeled in a traditional methodology. So given the fact that there was variation on constraints, the traditional methodology was missing or optimistically assuming that there is additional slack compared to reality. Then on top of that, we added in IR drop. So I'm just going to use PBA plus LVF plus IR. And this combination then reduced the slack as we would expect, because now you have lower voltage in most cases. And that gave us these couple of paths where the slack reduced significantly from 200 picoseconds down to about 10-ish picoseconds. And it turns out that that was the exact reason for failure, and those were the paths which were failing.
Because this is process variation driven, does this change depending upon it was done at this time versus it's going to vary further down the line with a different chip, or is it consistent all the way through that manufacturing run?
Yeah, so process variation, we account for global variation, local variation, all of that. There is also a new worry about aging of a chip, which I think is what you're referring to. And that in fact is a capability that can be added on top of this, where you can also look at aged versus unaged timing graphs and timing slacks. And some very advanced customers, specifically those who are servicing the automotive industry, have started to work with us on aging, because these chips have to last 10 years, beyond 10 years.
Typically, it's been the foundries that have been responsible for those kinds of aging models. Is that now being shared among a lot of different companies?
The foundries have absolutely the best data available in their PDKs. So they typically build reliability PDKs with the right models. But then there is a place for the tool to come in, look at that model, and analyze your paths on chip to give you an estimate of aged slack. And that's where vendors like us come in.
So what comes next?
Yeah, so while this is a great place to be, there are still concerns such as the voltage information that I'm passing into timing for this last graph that I drew is a point number. It's an effective DVD number from a dynamic simulation. Can that be a waveform? Can that be more accurate? That's something that we are researching. The vectors or the vectorless methods that are chosen to actually generate these dynamic IR profiles, can I increase the coverage so that you're covering more conditions in your chip? What does that require? That requires faster analysis tools. That's something that we are heavily investing in. So once we bring to market faster tools that will enable customers to do more coverage, reduce margins, and then get better, more accurate answers.
Ankur Gupta, thanks for a great explanation.
Thank you. Thank you, Ed.